Hello! Today I will show you how to generate from these sine waves these ringing tones. Then I will explain the piano software in detail. See you after the intro. These are the topics of today's video. How does a ringing tone look like and how do we create a ringing tone? Then I will explain the piano software in detail. Initialization of the interrupt routine, initialization of the tone generator, parameter passing, calculation steps inside the interrupt routine, start a new tone, and put the song in an array and how the play routine works. Then I will play 3 example songs on the Arduino Nano. I will close the video with a change recommendation of the filter capacitor in the digital analog converter, some notes to the software in the video description, and final remarks to the Arduino Piano. How does a ringing tone look like? In my last video I described how to generate a sine wave with a fixed amplitude. At the piano it is different. When we hit the piano string we have the maximum amplitude, and over time the amplitude decreases. And the decreasing shape is according to E function. The root cause for this decreasing is the internal friction of the string and the emission of sound energy to the air. In the computer we produce a ringing tone by multiplying a fixed amplitude sine wave with the E function and get a sine wave with a decreasing amplitude. This looks similar to the ringing tone of a piano. The decreasing E function will get by setting a fixed point variable to 1 at the beginning of a new tone and multiplies this variable with a factor less than 1 at each time step. Here an example with the factor 0.7. We start with 1, then 0.7, 0.49, 0.343 and so on, and we result in this decreasing E function. We define the duration of a whole note is 1 second. With a divider of 550 we will get the interrupt frequency of 29,091 Hz. For a 3/2 note we have a duration of 43,636 and a decreasing factor of 65,534. This is lower 2 bytes of the fixed point numbers or the decimal places of the fixed point number. 65,536 would be 1, so this number is a little bit smaller than 1. For a whole note we have 29,091 time steps for the duration and a little bit lower decreasing factor. And the list go on until the 1/32 note with a duration of 909 time steps and 65,372 decreasing factor. I will now 5 times play the concert A with no decrease and then 5 times the concert A with decrease. To get the same loudness impression I will play the non-decreasing tone with 1/8 of a second and the tone off part 3/8, and with the decreasing tone I will play it 3/8 and the tone off part 1/8, so the first part of the decreasing tone is dominant, and so this is very similar in the loudness impression. And another loop. Now to the detailed description of the software. We start with the initialization of the interrupt routine, especially the interrupt timer. We use timer 1 as an interrupt generator. This is an 16-bit timer and it is not used by the Arduino operating system. The setup should be as follows. The prescaler is set to 1. The timer should run up to 550. With 16 MHz divided by 550, we will result in 29,091 Hz interrupt frequency. We want no PWM output on the output pins, and the interrupt should be executed on each timer overflow. So every time when the timer reaches the value 550, it jumps back to 0 and an interrupt will be executed. The datasheet for the microcontroller used in Arduino Nano or Arduino Uno you will find on the microchip webpage with this link. Here we have the block diagram of the timer counter 1. The microcontroller clock comes via the prescaler to the control logic, and from the control logic it is fed to the timer counter register, which counts the prescaled microcontroller clock. The input capture register is in our application the maximum value register. When timer counter reaches the maximum value stored in the ECR register, the timer counter will be reset to 0. Here we have two output compare registers A and B, which are connected to dedicated microcontroller pins to generate PWM signals. We do not need in our application PWM signals, so we set these two registers to 0. Here we have the timer counter control registers. With the timer counter control registers we can define the function and the detailed behavior of the timer counter. We have three timer counter control registers, A, B and C. C is not mentioned here, but it is documented later in the detailed description for the timer counter registers. Now to the setup of the timer counter control register for timer 1 register A. With these 2 bits we can control how a compare match of compare register A with the timer counter is influencing the related output pin. With these 2 bits we can control how a compare match on the compare register B with the timer counter register is influencing the related output pin. Which action happens on the related output pins is defined in these tables here below. We want that the compare match has no influence on the output pins, so the compare register should be disconnected and the pins should remain normal port pins. So we select for compare register A 00 and for compare register B 00. In the program code we set the top 4 bits to 0000. The next 2 bits have no meaning, we will set them 00. And here we have WGM11 and WGM10. The definition of these 2 bits we will find on the next page on this table. WGM11 and WGM10. We want that the top value is defined by ICR1 and the top value should generate an interrupt. So we select function 14 and set the 2 bits to 10. So in the program code we set the 2 meaningless bits to 00 and the 2 other bits to 10. We go now to the setup of the timer counter control register for timer 1 register B. The upper 2 bits are for input capture noise canceller and input capture edge select. We do not use the input capture function and set both bits to 0, and the unused bit we set also to 0. In the program code we set the top 3 bits to 0. The bit setting for WGM13 and WGM12 we will find in the table we already know. Here we have WGM13 and WGM12, and for function 14 the setting is 1, 1. So we set in the program code the related bits to 1, 1. The bit CS10 to CS12 describes the clock source and prescaling. We want to have the microcontroller clock divided by 1, so we set the bits to 0, 0, 1. We set the 3 lower bits to 0, 0, 1. Now to the setup of the timer counter control register for timer 1, register C. With these 2 bits, in the non-PWM mode, we can force the related output on a compare match for channel A or on a compare match for channel B. We want no connection for the output pins to the compare register, so we set both bits to 0. The unused bits we set also to 0. So we set all the register C bits to 0. The timer counter register we initialize with 0. The interrupt frequency is defined by the microcontroller clock frequency divided by the prescaler divided by 1 plus stop. In our case the prescaler is set to 1, so it remains microcontroller frequency divided by 1 plus stop. The top value is in the ICR1 register. The top value must be 1 lower than the decided divider. For our example, if we want to have a divider of 550, we have to write in the ICR register 449. Max count is our decided divider, so we have to write ICR1 is max count minus 1. To clear all interrupt flags, we set TIFR1 to 0. Now to the setup of the timer counter interrupt masked register for timer 1. With these bits we can select which event triggers an interrupt. We want to have an interrupt when the timer counter register has an overflow and jumps back to 0. So we set the timer overflow interrupt enable bit for timer 1. This mask bit is at bit position 0, so we set here a 1, and at all other bit position we set 0. So we set for the timer interrupt mask register all upper bits to 0 and the lowest bit to 1. We want no PWM, so we set the related output compare registers to 0. We do not use timer 0 and timer 2. To avoid timing jitter by interrupts caused by these timers, we set their mask register to 0 and suppress interrupts by these 2 timers. Now I will show the initialization of the tone generator. In the file sinetable.h we have a sine table with 64 integer values. In the file notekey.h we have the symbolic names for the keys on the keyboard. K is the abbreviation for key, and the ending is the note. A0 is the note of the lowest key on the keyboard, and C8 is for the highest tone on the keyboard. For the black keys we have 2 names, because it could be either that it is a half tone higher than the white key, or it is a half tone lower than the white key. With enum we create a new data type called notekey_t, which consists of unsigned 8-bit numbers. Usually the symbolic names get beginning with 0 increasing numbers, so tone off is 0, K_A0 is 1, k underscore AIS0 is 2. Usually k underscore B0 becomes 3, but with the assignment equal to, the increasing numbering continue with 2, so k underscore B0 is 2, k underscore H0 is 3, k underscore C1 is 4, k underscore CIS1 is 5. Now we restart the numbering again with k underscore DIS1 is 5 and k underscore D1 is 6 and so on. With this renumbering, the black keys get the same number no matter whether the black key name is the increasing halftone or the decreasing halftone. We have two special values in the enumeration. One is tone off. It is for playing a pause or a dedicated silent interval, and it will be treated like a key. And the other special value is number of keys. We have here 86, 87, 88. The keyboard has 88 keys, plus the pause, which we handle like a key, is 89, and here number of keys is 89, so it is the size of the array which we need to hold the frequency information for all the keys. In video 27 I have explained how to create with a sine table, frequency count and sine table step the piano frequencies with high accuracy. In the file tonedata.h we have all the necessary constant for the tone generation. Our max count is 550, so we will lead to an interrupt frequency of 16 MHz divided by 550 is 29,091 kHz. Next we define the data type tone data underscore t. It has the entry sine table step. It is the step width where we step through the sine table, and frequency count is the number of digits we go forward on the interpolation line between two sine table entries. Next we create from tone data underscore t an array with number of keys entries. So we have for tone off and for each piano key these two data entries to define the exact frequencies of each of the keys. Here I have entered all the data from the spreadsheet from our last video. In the file tonegenerator.h there is the data type note time underscore t defined. It defines the length of a note. We have here 3 half lengths, 1 full note, 3/4, 1 half and so on. The coding is as usual. N3 underscore 2 gets the value 0, N1 underscore 1 gets the value 1, N3 underscore 4 gets the value 2, and so on until N1 underscore 32 gets the value 11. So we have from 0 to 11, 12 elements, and number of note times gets the value 12, which is equal to the number of note time elements. With note data underscore t, a note is completely described. Key is a key on the keyboard and defines the frequency, and note time is the duration of the note. Here we have additional two constants. No degrees is a 32-bit fixed point number with 16-bit decimal places and the value 1. We need this value when we want to play a sine tone with constant amplitude, and durations 1 second is the number of interrupts during 1 second. We have now discussed all the constants distributed over several files and come now to the tone generator file tonegenerator.cpp. In video 26 I have shown how to measure program execution time with timer 1. If timer 1 is used for other purposes, like in this piano application, it is possible to set and reset port pins and measure the time with the oscilloscope. I use here port B0, which is the Arduino Nano pin D8, and port B3, which is the Arduino Nano pin D11. To set the port, I make a logical OR connection with the related bit position set to 1. And to reset the port, I make a logical AND connection with the related bit position and 0. And here we have the same with port B3 set to 1 and a logical AND with 0. Usually we do not want these test outputs in the final code. Therefore it is a good idea to add a marker like test output on and do conditional compilation and add this code only when test output is on, and remove the code if test output is off or test output on is not defined. We go now to the setup routine of our tone generator. Setup tone generator. With the conditional compilation if def test output on, we set the data direction register B at position B3 and B0 to a 1, which makes these two pins two outputs. Then we set the data direction register D to FFX, which means that all the port pins D from D0 to D7 are outputs. And we can control via port D our R2R digital analog converter. Finally, we call our timer 1 setup routine with max count. Max count is 550. We continue with the parameter passing problem. The following must be considered. The data must be transferred completely to the tone generating interrupt routine, and when playing notes from an array, it must be ensured that the actual note is played completely before starting the next note. At an 8-bit microcontroller, it is only ensured for a byte operation that the data is stored completely in the variable. At 2-byte or more byte load operation, it could be that the load operation is interrupted by the interrupt service routine. Then only a part of the variable has the new data and the other part of the variable has the old data. If the interrupt service routine is then accessing to such a variable, nonsense data could be the output. Here an example for an incomplete data transfer of an integer number. We have here the main program flow, here the interrupt service routine calls, and here the output of the interrupt service routine. We have here the variable a, which will be initialized with the value 1111 hex, and during the program flow it will be alternating loaded with 2222 hex and 1111 hex and so on. With the assignment a is 1111, the Arduino Nano will first load the high byte of the variable a with 11, and in the low bytes there is still the value 22. In a second step, the Arduino Nano will the low byte also load with 11, and then we have the complete data in variable a. What is now the output of the interrupt service routine? At this position in the variable a is the value 1111, and the output will be 1111. At this position the high byte is 22 and the low byte is 11, so the interrupt service routine will output 2211. At this position we have still the value 2222 in the variable a, and the output will be 2222. At this position we have still the variable a with 1111, and the output will be 1111. At this position we have A 2222 and the output will be 2222. At this position in the variable A is 1122 and the output will be 1122 and so on. Here a test program which shows the problem on a real Arduino Nano. Here our timer 1 setup routine, and it is important to set up the timer 1 here with a prime number to ensure that the interrupt always happens on a different position in the main loop. And here we have the interrupt service routine, which will print out the variable A as a hex number, and here we have the main loop where we alternating setting variable to 1111 hex and 2222 hex. Now I will upload the program to the Arduino and now show on the output. I stop the auto scroll and we see here good value 1111 and here a good value 2222, but in between we have also bad values like 2211, and on the other position here we have the bad value 1122. There are several possibilities to solve the problem. One could be to suppress the interrupt service routine by loading the data into the variable A. But this has the disadvantage that the interrupt service routine is then sometimes delayed, and this will be a jitter on the sampling frequency, what is not good for our piano application. I will show you now how to ensure a complete data transfer with the help of a flag. We have here the main program flow. Here's a call of the interrupt service routines. And here's the output of the interrupt service routines. Data OK is our flag variable. If data OK is false, a new value can be loaded into the variable A. If data OK is true, a complete value is in variable A and the interrupt service routine can output the value. We initialize data OK with false and A with 1111. Data OK false means that the value in A is no valid value. Now the main loop begins. The first step is this while loop, but data OK is false and we leave the while loop and we get the assignment A is 2222 hex. In the first step the high byte will be loaded into the variable A. Now the interrupt service routine is called. The if condition data OK is false, so we jump over, we have no output and leave the interrupt service routine. Now the low byte part of the variable A is loaded. Data OK is set to true and we go into this loop because data OK is true. The interrupt service routine is called and now the if condition is true and the variable A will be output on the screen. Data OK will be set to false and we leave the interrupt service routine. Due to the fact that data OK is now false, we exit the while loop and come to the assignment A is 1111. First we load the high byte into the variable A. If now the interrupt service routine is called, the data OK is false and this part is jumped over and no output on the screen. We leave the interrupt service routine and the low byte of the variable A is loaded into the variable A. Data OK is set to true and we are now in this while loop. The interrupt service routine is called. Now the if condition is true because data OK is true and we output the value 1111 and set data OK to false and leave the interrupt service routine. Now data not any longer okay, we exit this while loop, and the new assignment A is 2222 begins, and now the whole story starts over again. Here our second example. We have here our timer 1 setup routine. We call the timer setup routine with a prime number to ensure that we get not in a synchronized state with the main routine. We have here our flag variable data OK, which we initialize with false, and our variable A, which we initialize with 1111 hex. In the interrupt service routine, we do only the output if data is okay, then we output the variable A in hex form and set data OK to false. And here is our main program. We wait until data OK is not true, set the variable A to 1111 hex and set data OK to true. And here we have the second loop. We wait until the data is not any longer okay. The variable A will be set to 2222 hex and data OK will be set to true. And this is in our endless loop to repeat this output. Now I load the program to the Arduino. And then we will look on the output. And now we see, I stop the auto scroll, that we have only valid numbers 1111, 2222. We see also that the numbers are always alternating. We have it synchronized to the main program, and we see we have no bad values 2211 or 1122. We have now seen how to ensure that the data is always transferred completely to the interrupt service routine, and with the same trick of a flag we can ensure that the tone is completely played before the next one is started. Now the calculation steps in the interrupt service routine. Here are the transfer variables to transfer the data from the main program to the interrupt service routine, and the flags to ensure complete data transfer. All variables are marked as volatile. This is that the compiler did not any pre-assumption of the contents of these variables due to preceding calculation steps. The variables can change their value all the time because there are two parallel processes which have access to these variables, the main program and the interrupt service routine. With the flag variable load new tone available, the main program tells the interrupt service routine that in these four variables a complete new tone is available. And with the flag variable loaded tone active, the interrupt service routine tells the main program that the actual tone is still in process. With load sine table step width and load low frequency count, the frequency of the tone will be set up. With load decrease factor, the decreasing time will be set up, and with load tone duration, the complete duration of the tone will be set up. Now let's go to the interrupt service routine. Variables with the mark static will hold their values over the complete program execution time. The other variables hold their values only while the interrupt service routine is active. With port B0 we measure the execution time of the interrupt service routine. At the beginning we set the port B0 to 1, and at the end of the interrupt service routine we set port B0 back to 0. With port P3 we measure the frequency we step through the sine table. At the beginning we always reset port P3, set it to 0, and when we have a step in the sine table we set port P3. The first step we will do is output the value of the last calculation to port D. Port D is our digital analog converter with the R2R network. This will ensure that our output sampling timing is always constant. If we would do the output after we have calculated within the interrupt service routine caused by the if statements, we will have different execution time, and there will be a jitter caused by the different program execution time on the sampling frequency. When a new tone is available, we set the internal variables to the new tone data, initialize the sine pointer to 0, the frequency pointer to 0, the loudness factor to 1, and we set the new tone is active to true, and we set the load new tone available to false to avoid on the next interrupt that we initialize again the tone. When the decrease factor is smaller than 1, we calculate loudness factor times decrease factor and take the upper 16-bit for the new loudness factor. It is important to know that if the decrease factor is 1, that we cannot do this calculation because then we will get an overflow condition. Now to the frequency calculation. A detailed description of the frequency generation you will find in video 27. Here I will only describe some program-specific details. We store our actual frequency pointer, and then we add to the frequency pointer the low frequency count. And as we already mentioned in the last video, the overflow will handle automatically the subtraction of 65,536. But we must recognize the overflow condition. This is done when the frequency pointer new is lower than the frequency pointer last. In this case, we step one step further in our sine table, and we set, as already mentioned, the port 3. Now we come to the weighted start sample and weighted end sample. The weighted start sample is 1 minus frequency pointer times the actual sine table entry. The weighted end sample is frequency pointer times the sine table entry one step width further. We add now the weighted start sample and end sample to get the sine wave at the position frequency pointer and multiply it with the loudness factor to get the ringing tone. And for the output, we take the upper 8-bit and add 128, that the sine wave is swinging around the plus 2.5 volt, so the most negative sine wave is 0 volt and the most positive sine wave is 5 volt. Finally, we have to check the tone duration. If tone duration is bigger than 0, we decrement tone duration by 1, and if the loaded tone is active and the tone duration gets 0, the tone is ended. For this, we set the loudness factor to 0 and the loaded tone active to false. And as already discussed, we reset port B0 to saying the end of the interrupt service routine and leave the interrupt service routine. Start a new tone. There are two ways to start a new tone. The first is the immediate start. This is important when you play music on a keyboard. Whenever you press a key, you want to immediately hear the new tone. The subroutine load new tone will load sine table step width, low frequency count, decrease factor and tone duration into the transfer variables and set the loaded tone active and load new tone available to true. So with the next call of the interrupt service routine, this new tone will be activated immediately. The other way to start a new tone is with the routine wait load new tone. It waits while the actual tone is active. When the actual tone has reached its end, the loaded tone active is false and a new tone will be loaded to the interrupt service routine. This routine is the right routine to play music out of the memory. From these two basic subroutines there are several variants with different parameters to start a new tone. At the subroutines load new tone and wait load new tone, there will be transferred the name of the key, the duration and the decrease factor. The routines load new note and wait load new note exist two times and differ in the transferred parameters. You can either transfer the key name and the note time, or you can transfer the complete note which contains the key name and the note time. And here internally the data will be transferred to the key name, the duration count and the decrease factor, and the originally load new tone routine or wait load new tone routine will be called. And the headers of these subroutines are published in the tonegenerator.h file that other program parts can use it. Put songs in an array and the play routine. For a better program structure, I have put the data for the songs in separate h files like here, here and here. We generate from the data type node_data_t an array with the name of the song and square brackets without the size information. So the compiler will automatically adapt the size of the array to the data what we put here in the array. The single notes are written in curved brackets with the key name and the note time, and each of these notes are separated by a comma. If we need a pause, we write instead of the key name tone off and also the note time. And the complete array has here a curved bracket open and at the end a curved bracket closed with a semicolon. To get the separation of the three songs, I have written on each end of the songs some tone off notes, so we will have a silent pause between the three songs. And now to the main program. As I already mentioned, the compiler defines automatically the size of the array. But how can we now find out how many nodes in the array? To get the number of nodes, we define the macro array size. X is the complete array, size of x is the number of bytes of the complete array, size of x square bracket 0 is the number of bytes of one node. So if we divide the complete size with the number of bytes of one node, we will get the number of nodes in array size. Here we include the three files with the nodes of the songs, and here we place the three songs. We have here the index variable tone. It runs from 0 and will be incremented by 1 as long as tone is smaller than the number of elements in the song. Each tone of the song will be played here. And this will be done for the song Alle, meine, Entchen, for the song Hänsel und Gretel, and for the song Ein Vogel, wollte, Hochzeit machen. So let us hear the music. Alle, meine, Entchen. Hänsel und Gretel. Ein Vogel wollte Hochzeit machen. a note on the filter capacitor. In the video 023, the R to R digital analog converter, I specified a filter capacitor of 2.2 nanofarad. Due to the lower sampling frequency as originally assumed and the relative flat curve of the first order filter, significant harmonics can be still heard with the 2.2 nanofarad capacitor. To avoid this, instead of the 2.2 nanofarad, a 100 nanofarad filter capacitor should be used. Some notes to the software in the video description. Due to the limited space in the video description, the software for the piano is distributed over the videos 27 part 7, 28 part 8a, 28 part 8b and 28 part 8c. The videos 28 part 8b and 28 part 8c have no new content. They are only there for distributing the software in the video description. Comments to the software in the video description text below. The video description text did not accept the characters lower than and bigger than. Therefore, these characters are replaced by the strings _LT_ for lower than and _BT_ for bigger than. After you have copied the program code from the video description text into the Arduino development environment, you have to deselect here Bearbeiten or Edit and here Suchen or Search or Find, and then you get this input box and you have to put here _LT_ and in the second line the lower sign and select replace all, and then we have to write here _BT_ and select here the bigger sign and replace all, and then you can close the box and upload the program. In case the program make output to the serial monitor program, the baud rate in the serial monitor program selected here must be equal to the bit rate selected here in the setup routine for the serial begin statement. And the same if the program make output to the serial plotter program, then in the serial plotter program the baud rate selected here must fit to the bit rate selected here in the setup routine at the serial begin statement. The Arduino Piano is now in a state where we can use it. We can play stored songs. The keyboard input I will show later. This is due to some interesting topics I will show in the next videos. About feedback I would be happy. How have you liked the Arduino project so far? Or which topics are you interested in? That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. See you in the next video. Bye bye.